multi-aspect into useful information and predictive models that support environmental and urban decision-making with high accuracy. This is the core purpose of our training program. We move beyond map users toward becoming producers of spatial intelligence using ArcGIS Pro, not as a mapping tool, but as a comprehensive analytical environment. The training follows a four-stage of workflow reflecting real-world spatial data science from data collecting and pre-processing to modeling, prediction, and automated analysis. Our first session for today will be about fundamentals of satellite image processing. The second session will round about advanced classification techniques. And the third session will be about temporal monitoring and dynamic analysis. The fourth session and the last one will be about hydrology and workflow automation. Together, these models guide you from interpreting imagery to producing scientifically strong and reliable geographic knowledge, moving from observation to prediction in alignment with modern research standards in GIS and remote sensing. Today, as we mentioned, we will start from the optical and numerical basics because every successful analysis begins with understanding the image itself. To interpret any satellite product, we must first To interpret any satellite product, we must first understand how the image is formed, what information each band carries, and what limitations influence the data. In other words, we begin by learning the language of satellites. Why this session matters? Because pre-processing is the essential scientific step that transforms raw imagery into reliable data. Our session established the foundation upon which all advanced analytical skills depend. Without a solid understanding of pre-processing, any later analysis will rest on a weak base. Raw satellite images can't be used as they are. They must be corrected, enhanced, and standardized before they are scientifically valid. Once pre-processing is complete, we move on to extracting meaning, making pixels speak through multispectral analysis, spectral transformation, and quantitative indices that help us detect temporal change and assesses vegetation health and water resources. Our goal today is to convert raw satellite imagery into accurate, scientific sound data sets ready for interpretation. Throughout the session, we will address key questions. How does satellite image actually work? Why can't we use the image as it is? And what corrections are necessary to ensure high quality analysis? We will develop a clear understanding of satellite image fundamentals and major satellite missions such as Sentinel, Landsat, and MODIS. We will learn the required pre-processing steps that guarantee the quality of any future analysis. And we will gain the ability to extract key spectral indices as well as image enhancement techniques for assessing vegetation health and resources and water resources. Now, imagine you are looking on a lake. You see the blue water, green plants along the edge, and the dry land around it. This is the image as our eyes perceive it. But what if I told you that there's another image hidden from human sight? In this image, healthy vegetation allows bright red, glows bright red, water appears as deep black, and built-up areas shows as play gray. This is how the satellite perceives the scene based on physical reflectance properties. So beyond the visible, how satellite sees, human eye sees only visible lights, while satellites utilized multiple spectral bands, example of near infrared and ماشي الزوم عندكم مين فاتح؟ yeah. بس أنا بعده ماشي عند الزوم ماشي الحال ماشي. اوكي بس بدون سؤال هنحصل على الباوربوينت هنحصل على الباوربوينت no في a guide I will receive for you will send for you okay طيب to understand this let's return to a basic concept لا في عنا الإلكترون To understand this, let's return to a basic concept. We see because light reflects off objects into our eyes. However, the light we see, red, green, and blue, is only a tiny part of what is called the electromagnetic spectrum. Satellites are equipped with sensors that can detect other parts of the spectrum, such as near-infrared and shortwave infrared. Each part of the spectrum is recorded in a separate layer called band. Here comes the concept that will change the way you think about satellite images, which is the spectral signature. Every material on Earth, where vegetation, water, soil, has a unique pattern of light reflection across different bands. Healthy vegetation, as shows, strongly reflects near-infrared light while absorbing red light for photosynthesis. This contrast is its unique signature. While water absorbs most infrared light, appearing very dark in near-infrared bands, and the bare soil reflects light moderately across most bands. These spectral signatures allow us to see what the human eye can't, and are the key to quantitative analysis. These differences enables us to distinguish the different surface elements without physically touching them. What is a satellite image? A satellite image is not a photograph. It is, in fact, a digital representation of how energy is reflected. Each point in the image, called a pixel, carries a numerical value known as a digital number. This number records the intensity of radiation captured in a specific band. When a satellite captures an image of a field, it doesn't record the green color, but it records numbers. For example, the field might have values like 1,500 in the red band and 2,300 in the near-infrared band. And each successful classification starts with understanding the digital numbers don't represent the surface itself, but the sensor's response. Our task is to convert these values into a unified physical scale. The quality of any subsequent classification depends on understanding this digital representation of each data.
بس pardon, فيك تشيل الصور لما عم تروح نص الصفحة. Thank you.
اوكي. كنت تقولوا لي من الأول مش مطلعة فوق. So the key question is, do these numbers tell us the true reflectance of the surface? And the answer is no, which highlights the importance of pre-processing. Why? Because digital numbers are influenced by, first, sensor sensitivity, which each satellite has its own characteristics. Also, acquisition time. The sun angle differs in the morning and at noon. And the DN values affected by the atmosphere because clouds and dust affect the light. The distance of the sun changes throughout the year. That's why DN digital numbers values are not reliable. To merge for the satellite image, every satellite image is characterized by 4 fundamental resolution types that determines its capabilities and applications. First one, we want to talk about spectral bands. Each band captures light within a specific wavelength. Some bands are visible, like red, green, and blue. Others are invisible to a human eye, such as near-infrared. Each band provides different information about the surface, as we said, about vegetation and about soil. The second resolution must be in any imagery is the spatial resolution. Here we talk about the size of each pixel on the ground. That means smaller pixels equal more details. And the spatial difference equal 10 meter is higher resolution than 30 meter imagery. This determines our ability to monitor change over time. That I talk now about a temporal resolution, which how frequently the satellite revisits the same location. Each satellite revisits the same location by varied period. Some satellites revisit the same place every 5 days as a Sentinel, and others revisit every day like MODIS. Then the fourth one is radiometric resolution, the number of digital levels the sensor can record to distinguish different differences in reflecting energy. Together, these properties define the type analysis that can be performed and the reliability of the result. And to select the satellite, selecting the right satellite is the first step in any scientific study. The satellite must match the researcher objective in terms of spatial and temporal resolution. First, we talk about Sentinel-2, the expert, which offers a high spatial resolution, 10 meter, and excellent temporal resolution every 5 days. As I said, Sentinel-2 revisits such location every 5 days, making it ideal for monitoring vegetation, water, and early detection of change. The data availability was from 2015 till now, and the number of bands is 13 spectral bands, providing every rich information. The second satellite is the Landsat, and we can say about it the historical archive. It provides data spanning decades, making it invaluable for long-term time series studies extending 30 plus years, despite its lower spatial resolution, which is 30 meters. MODIS, known for its daily temporal resolution, suitable for rapid monitoring and early warning, such as tracking flood and wildfires. Although its spatial resolution is lower, ranges from 250 to 1,000 meters. Now, choosing the satellite must depend on spatial resolution, as we said, the level of detail captured in each pixel, and temporal resolution, how frequently the satellite revisits each location. And also, choosing the satellite depends on purpose of the study, the specific application and analysis requirement. So, for example, if we want to study rapid crop monitoring, Sentinel is suitable. And if we want to study 40 years historical records, the Landsat is best option. And for daily flood alerts, MODIS is preferred one. So each satellite serves a specific purpose. We must mention that satellite imagery is provided in different processing levels. First level is L0, which means this data is raw and unprocessed. The L1, level L1, the radiometric and partial geometric correction. There are subtypes under the L1 and L2, fully atmospherically corrected surface reflectance. For scientific analysis and temporal comparison, L2A is the preferred level because it provides accurate analysis-ready reflectant data. On the other hand, a satellite captures multiple images at the same moment, each representing a different part of electromagnetic spectrum. This is what we say multispectral data. Imagine having several cameras. One sees only red light, one sees only green, and one sees only blue. A satellite does exactly this. It carries specialized sensors, each capturing a specific spectral band. Different satellites record multiple bands, each covering a distant wavelength range: blue, green, red, near infrared, or others. And every band reveals different information about vegetation or build-up areas. Multispectral satellites like Sentinel and Landsat have a limited number of broadbands, sufficient for most environmental analysis. Hyperspectral sensors capture hundreds of very narrow bands, enabling highly detailed identification of materials. In summary, when we talk about multispectral imagery, that means it provides rich, practical information and is ideal for our training tasks, while hyperspectral imagery enables highly specialized scientific analysis, but requires more complex processing. Why pre-processing is critical? Look or imagine you have a satellite tool or a Landsat image. Can you see it directly? And the answer is no. Pre-processing is the most important stage of remote sensing. And without it, any spectral index or classification will be unreliable. Pre-processing transforms this raw satellite data into reliable, analysis-ready information, and it is the foundation of accurate remote sensing, which removes the distortions, which mean elimination sensors and atmospheric errors. Also, it enables temporal comparison, makes images from different days comparable, and also it ensures accurate spectral indices, provides reliable vegetation and water indices. About 70% of classification accuracy depends on proper pre-processing. There are three main categories of distortions that need corrections: the radiometric, the atmospheric, and the geometric. We will start first by talking about the radiometric distortions. Now, suppose you image the same field twice. First, we take an image on March 15. The sky was sunny. And the second image was on March 20. The sun is slightly lower and some atmospheric dust found. Even though the field hasn't changed, but the digital numbers valued can differ by 30% more, making direct comparison and temporal analysis unreliable. The cause of radiometric distortions is why, when sunlight reflects from the surface toward the satellite, the recorded DN values don't represent the true surface reflectance due to what? Due to sensor sensitivity difference, due to atmosphere effects, and due to sun angle variation. That result, pixel values for the same location can differ significantly between images taken at different times. This solution will be by radiometric calibration. This process converts digital numbers into reflectance, producing physical values that reflect actual sunlight reflected from the surface. So the radiometric calibration ensures that the same pixel in two different temporal images represent the same real-world value. In ArcGIS Pro implementation, we can apply this by the raster calculator from analysis tools raster calculator. Enter the expression for each band, float the name of the band over 10,000. The outcome, bands are more consistent now. Pixel values represent true surface reflectance. When we talk about the atmospheric distortions, that's why when we capture satellite imagery, the atmosphere modifies what the sensor records. Dust, aerosols, water vapor, and gases can absorb and scatter light. Rayleigh light scattering affects shorter wavelengths like blue, while my scattering affects larger particles such as dust and aerosols. Gases like water vapor and ozones absorb specific wavelengths, reducing the signal reaching the sensor. And also, we can say that coastal regions are particularly affected by humidity and sea fog, making images appear hazy or washed out. To correct atmospheric distortions, we use atmospheric correction. The simplest method is dark object subtraction, or DOS, which assumes the darkest pixels, such as deep water, should have near zero reflectance. This method removes the scattering caused by aerosols. In ArcGIS Pro, you can apply the correcting the image this way, ensure we obtain accurate surface reflectance, essential for quantitative analysis like vegetation indices or cover classification. Whenever possible, it's better to use L2A surface reflectance products as they come with atmosphere correction already applied. And in ArcGIS Pro implementation, we can open the raster calculator and apply the subtraction of each band minus the dark pixel value. Satellite images are rarely perfect. They are affected by the Earth's rotation, changes in the satellite's path and altitude, terrain variation, and lens distortion. This means that a point on the ground might appear hundreds of meters away from its actual location. And the geometric correction aligns the image so that every pixel matches its true ground location. This step is essential before performing any analysis, including multi-temporal comparison or change detection. There are three main types of geometric correction. Registration aligns an image with another image, useful for temporal comparison. Rectification aligns the image to a known map or coordinate system. Orthorectification is the most accurate. It uses a digital elevation model to remove terrain distortion, increasing that, or we can ensuring that pixels are located exactly where they should be on the ground. This geometric correction can be performed using two approaches, the systematic approach and the empirical one. The systematic one uses satellite telemetry and physical data. No ground points are needed, while the empirical approach uses ground control points or GCPS. There are points with known coordinates visible both in the image and reference map. They should be disturbed evenly across the image with at least 4 points or maybe 6 to 8. we must ensure the good control points. We can choose road intersection or building corners, and the poor ones include white field and maybe a dynamic shoreline or clouds. Geometric properties with DEM using a raster function in ArcGIS Pro. We can open raster function, and from the analysis, we can choose the geometric properties, apply geometric properties using a digital elevation model. The input raster was selected as you studied. And we must input the reference digital elevation model. Without this step, pixels may appear in the wrong location or have incorrect spectral values, making NDVI or classification unreliable. We must mention that using geometric properties with a digital elevation model does not fully correct geometrically distortions like ground control points, but ensures cell size, extent, and origin alignment with the digital elevation model. It's essential before any temporal analysis or raster calculation across multiple years. The cloud masking, clouds and their shadows can severely affect the quality of satellite image analysis, causing misclassification or reducing accuracy. For multi-temporal analysis, can apply the same masking approach to all dates, and L2A cloud masking is more accurate due to the availability of SCL. And if we use the L1C masking, that depends on your thresholds, which result may vary. The goal is to exclude cloud covered and shadows pixels from analysis. That applied in the ArcGIS Pro using the raster calculator and applying the conditional expression. For Sentinel-2 L2A images, we use, as mentioned, SCL to identify cloud pixels. And if SCL is unavailable, as mentioned in L1C, near infrared and cloud probably rule. Clouds remain bright in both near infrared and the rule assumes non-cloud features, اللي هي soil, vegetation, water, become darker in SWIR, could remain bright in both near infrared and SWIR. Before every analysis or application, the image enhancement can be divided into a visual and analytical technique. First, that technique for visual improvement can use the contrast stretching that improves how clearly we see features without altering the actual data, using tools like percent clip in the appearance tab. The second one is the smoothing and sharpening, enhance edges and reduce noise, making details more visible. To enhance the image visually in ArcGIS Pro, we start with contrast stretching, go to appearance tab, a stretch type in the rendering group, choose a stretching method and the percent clip, which example can use the extreme value 2%. This make details that were unclear before now more visible. The second one, sharpening, we can open raster function pane, convolution, select your input raster, choose a kernel filter type sharpen. These enhancements help us interpret the image more clearly without changing in the underlying data value. Haneen, please do show me. Resampling is necessary when satellite bands have different spatial resolution. For example, Sentinel bands 11 and 12 have a lower resolution than bands 2, 3, and 4. We resample. We resample to ensure all bands align and have the same cell size. The choice of method depends on the data. The nearest neighbor preserves values for categorical data, while bilinear is good for continuous data with a smooth interpolation. And cubic produce even smoother results with enhanced visual quality. In ArcGIS Pro, go to Data Management, Raster, then Resample. Open the Resample tool and set the input raster, the band you want to study, set the output raster, and set the cell size. You can set it 10 meter as the smallest one as band for example. PCA is a statistical technique compresses multiple correlated bands into fewer uncorrelated components. The outcome, PC1, captures the most variance, while PC2, PC3 reveal subtle or hidden features that may not be visible in the original band. It reduces noise and increasing class separability without changing original pixel values, but makes the imagery more efficient for classification. In ArcGIS Pro, we can use the search about the principal components and put the bands, then we have the output. Now we can transform or move from raw to analysis. We start by merging individual bands into a single multi-layer raster using the composite band tool. For display, we can choose 3 bands at a time. So the objective, merge individual bands into a multi-layer raster for analysis. The benefits, speed up analysis, enables spectral analysis and the transformation, and the displacement. We can use band combination type to have the nature color or the false color. What is the true color, which is a natural looking image using the visible spectrum bands? Red, which is band 4, green, which is band 3, and blue, which is band 2. A true color is useful for general interpretation and mapping, show water, vegetation, and soil in a familiar color. False colors is ideal for vegetation analysis, highlight healthy vegetation in bright red, while stressed vegetation appears pink, and we can detect water delineation and burn detection. This is a key first step for a spectral enhancement. For visual clarity, use contrast stretching via the appearance tab with percent clip, which doesn't alert the data. From bands to quantitative analysis, we move from raw to analysis, and then we can move from bands to quantitative analysis. Spectral indices convert band values into quantitative measures of environmental features to extract a specific surface information. We can talk about NDVI vegetation, that is normalized vegetation index, measure the plant health and density. Highlight, as mentioned, the vegetation health with higher positive values indicating dense, healthy plants. NDWI identifies water bodies and moisture content, and NDBI detects urban surface. We calculate these in ArcGIS Pro using a raster functions or raster calculator. By using indices, we move beyond a simple visual interpretation, giving our image measurable information that can guide research and monitoring. Band ratio are one of the earliest and most reliable way to enhance spectral information by dividing one band by another. We highlight how different materials reflect light differently. For example, the near-infrared over red ratio enhances vegetation because healthy plants strongly reflect near-infrared. And custom ratio are powerful when standard indices don't capture the phenomena, such as mineral signatures or specific soil types. In ArcGIS Pro, we simply use a raster calculator to build any ratio we need. The effective use now is a simple temporal change detection. Helps us to identify how an area has evolved between two dates. We rely on simple delta index, subtracting the older NDVI map from the newer one. For a valid comparison, both images must come from the same sensor and undergo identical radiometric and geometric correction. NDVI change detection. After computing NDVI for each year, we must subtract, as example, NDVI for 2015 or 18 from NDVI 2025 using raster calculator. The output positive values indicate vegetation improvement, while negative values show degradation. We can reclassify these data by reclassification, which help us distinguish major loss, stability, and recovery zone. These results guide us toward environmental hotspots that may require further investigation. Always, it ensures the correct near-infrared and red band are used, band 8 and band 4 if we use Sentinel 2, and apply cloud masking if large zero variable patches appear. For advanced application, now that we have a quantitative NDVI map, we can use them in applied analysis. Suppose the research objective is to examine how vegetation health varies with the lake. To start, we need to isolate only the healthy agriculture zone. using raster function, local, and map algebra. We apply a simple conditional expression, conditional NDVI map greater than 0.5. This converts the NDVI raster into a binary map. Pixels with NDVI above 0.5 become 1, representing dense and healthy vegetation, while all or other pixels become 0. The resulting layer isolates the productive agriculture area. From here, we can calculate their total area or use the binary map as input for more advanced modeling, such as proximity to lake, buffers, or environmental risks. Here, I want to end this session with applying these tools inside the center. And I hope to meet you again next week, inshallah. طفي الزوم يا
خلصتي دكتورة زينب؟
نعم دكتور.
I would like to thank Dr. Zainab for this valuable and informative lecture. You can send your question via email and thank you for attending, and we'll see you next week inshallah. For the certificate should participate in all 5 sessions plus a homework assignment. Okay, thank you and see you next week, inshallah.